So we're using the ACE engine to convert. But what does that intent thing mean? Well, I've brought up our little ICE 1931 color space, and I've doodled out about what the Adobe 98 color space is as compared to the SWAP CMYK. Notice the SWAP's smaller. So first off, the ICC is the International Color Consortium. They're the ones that came up with the ICC profile, which is this set of data that characterizes color's input or output device or a color space, and they have standards for that. Now, they kind of worked out what the intent is. The idea was that the process of bringing colors from a larger color gamut like the Adobe 1998 to a smaller color gamut like the SWAP CMYK, or honestly most RGB to CMYK devices, they figured that there should be 4 methods implemented, and they referred to these methods as rendering intents. And they started with essentially 2 colorimetric intents, absolute colorimetric. I keep wanting to mispronounce that one. Absolute colorimetric and relative colorimetric. So the colorimetric is just reproducing an image colorimetrically, so essentially trying to map the colors on top of each other as accurately as possible between these 2 color spaces. But it's going to result in vibrant colors outside of the smaller color range. So for example, these greens that the Adobe 98 can cover without a problem, they're outside of the gamut of the SWAP. If you have a printer that's capable of SWAP CMYK style stuff without any issues, you got a whole bunch of greens that just aren't going to be represented. And we saw that when we switched over the snail. If we just flat out go mode CMYK and ignore all of its warnings, we can see that the original had much more vibrant greens than the final one. And that makes sense looking at these metrics. We don't have as many greens available to us in the SWAP, even the SWAP version 2. So what's happening is they're being clipped down to the same color. So the idea is that if it's out here, it's going to somehow be pushed down and either clipped to this, or you're going to do something a little more interesting. So let me talk about that a little bit. So you've got the absolute colorimetric, and this is usually used for proofing and will simulate a commercial printing press with that has a large gamut. But out of gamut is typically not an issue, except for really bright things like flowers and sunset photos. But it's going to probably add a tint to your white to simulate paper, so it's doing some weird stuff. It's not doing any compression by default to the black, so it tries to leave them alone, but it's pretty poor for photographs. But what is the absolute colorimetric? Well, I've got a little drawing here that I'm going to reproduce for all of you. Get the default color with the D key to get this black. Grab my pen. Let's say we have a color out over here. And actually I'm going to make that a circle instead of a dot, just so we can get a better idea. So we've got some color out over here. Now, it's fine in Adobe 1998. It exists without any issue. But inside the SWAP, we have to make some decisions. We could just pull it down to the maximum green allowable in SWAP. So it's essentially clipped down to a green. We just slit it. And that's true for any of these. If you had like this kind of tealish color, it would be pushed down right over here, period. It gets as close as it can. Have this nice blue, well, that's outside. We're just going to clip it to whatever's going on here. So there's not any real compression going on. It's just clipping. It's bringing it over as close as it can, and then it just gives up. That's it. So that one is the absolute colorimetric. I don't think I've mixed that up. My notes are a little smudged right here. I always try to get this part right. So let me double check that. It shouldn't have any compression. Let's see. Vibrant colors are clipped down. Yeah, so that's the absolute. So basically, if it's just outside like this yellow, it's just going to get clipped down, and then that's that. Everything else inside of here, if for example you had, I don't know, this kind of tangerine style color right over here, that's not going to move, right? That just exists in that space because it exists within both spaces. So it just sits there and it's fine. So there we have it. But what about a relative color metric? I'll just call that abs. So we have another way of handling this, which is interesting. So the relative color metric will map the white point of the image relative to the original. So the white point of the original color space, for example, Photoshop's working space, will be matched to the output's color space, like the printer's profile, whatever we load in there. The other colors will be scaled appropriately, so it's going to be compressed in a bit. This works well for printing photos on glossy paper. It's going to do a pretty good job. Now this is weird. Let me talk about this one. So before, with the absolute, you just push it straight in, or if it's outside, you just leave it alone. If it's already in there, it's already in there and it's perfectly happy and it's not going to have any issue whatsoever. Now and there we go. Okay, and so, whoa. All right. So we have about the same colors, right? Let me go ahead and circle out about the same colors. I think I missed one. There we go. So we've got about the same colors on our relative. So I get out the paper here. On the relative color metric, it will map the white point of the image relative to that of the original. The white point of the original color space, like Photoshop's working space, will be matched to the outputs of the color space, so the printer's profile. The other colors will then be scaled appropriately. So this works well for printing photos on glossy paper. Now, keep in mind this is going to do something. So let me explain what's going on there. So if you've got a color sitting inside of the gamut, it's going to be left alone. But it's trying to do this cool thing. Boop. Where it figures out based off of the white point of, say, the light of Adobe, or the white point of, say, a piece of paper, which is much, much duller than the white point of a monitor coming out. It tries to figure out how far away it is from that point as compared to the where the other point would be, and then it moves it in a relative amount. So if from here to the white point is like, I don't know, some arbitrary number like 37. I don't know. It's not a real number. So it's going to go in and go, well, what's the ratio then here as compared, because the white point's in a slightly different position. So it would bring it in and go, in this universe, 37 would be about here. So in other words, it goes, this is X amount from the white point. So now this will be X amount from the white point, where, all right, so let me explain this a little further. You can only go so far out from the white point, yeah? Then you've hit the edge. That's as far as it can go. So there's some distance that's 100%. So really this would be like 90% maybe of the distance, right? So now on the new white point, you have it coming out. You have to go, say, 90%. So really that would be like about over here. So you'd get about 90% of the distance from the white point. Now, if it's within the color gamut, it's actually going to leave it alone. So it will pull everything else in, measuring out from how far that white point is as compared to the new location of the white point. Now, that's a pretty cool concept, but now you've got something strange going on. You're going to have a different appearance of color, because now some things have moved, but other things have not. So it's not going to look the same, right? And so that brings in from relative color metric to perceptual. This is changed from software to software. It attempts to pull the out of gamut colors in, as determined by the printer profile, into gamut relatively. The ratio from the outer gamut edge should be perceived in the inner gamut's edge, and it's an attempt to reproduce how a human would view it in the two environments. And if you do a quick, that sounds a lot alike, right? But if you Google relative metric color relative colorimetric versus perceptual, you're going to get this pretty sweet little reminder. Relative colorimetric changes all of the colors out of gamut to the nearest color in gamut. So many colors change to the same one, and it will not change colors in gamut. Perceptual changes all of the colors in an image proportionally so that they lie in the printer. So in other words, remember how we were moving in, but we left this guy alone because it existed in both positions? This little guy would just exist right here. This would be relative. Yeah, so it existed before, it exists again. Something different happens with the perceptual. And that's this. So let's start again with the original colors. Really, I should have just started by duplicating this. So up and turn off these guys so we can see what we're doing. That's not a very good duplicate at all. There we go. So we have the perceptual. Now what it's going to do this time is look at the edge of the color gamut and say, okay, how far in have you gone? So it's figuring that out. Like, let's say it's figured out some percentage away in some direction, and it's going to need like multiple directions, which is why it's going to change from software to software. What I mean by that, well, this outer bit is a triangle, right? But this inner one is some crazy trapezoid shape. So you can't just say, you know, this far on the triangle, it's this far in. That's not going to work because that doesn't translate well to inside of this weird geometric shape going in. So that's why it changes from software to software. They're doing some crazy mathematics on everything. But basically it's this. It goes, you're some percentage away from the edge. You're also some percentage away from the edge. You're some percentage away from the edge. What this perceptual is concerned with, and it does that for all of them, is what percentage away from the edge is the new location going to be. So it tries to duplicate that. So it kind of rubber bands everything in based off some cool math, but it's going to end up wiggling things a little bit even if it was inside of the color gamut, because there's going to be a slight difference between these gamuts, right? They're not precisely mapped on top of each other. So all of a sudden you have slight motion going on everything. Nothing is sacred. Everything gets moved slightly. But what does this mean to us as humans? Well, the ratio of things from the absolutes have stayed about the same. So sure, we shrank it in, but we shrank everything in. And so that's our perceptual intent going in. Now there's one more. You have the saturation, and that just pulls any of the that just pulls any of the out of gamut colors saturations down until it's in the gamut of the other one. And so this can result in oversaturated colors collapsing in on each other and looking really flat, but it will preserve the saturation on any in-gamut colors. So essentially, if you, in this one, did I have that's the wrong one. On this one, just for saturation, we'll just call that sat. If you have a color out here, and we'll just simplify this. If you have a color out here in Adobe RGB and a color here, it would leave this color alone. It's perfectly fine, but it will be unhappy with this color. So it would adjust the saturation, and we've seen some of the ways Adobe can do that. They have something called hue and saturation. They just grab the saturation and drop the saturation down until at some point it will be inside the smaller color gamut. So it's not going to do that to everything, though. It's only going to do it to the out of gamut colors. So this guy's going to get duller and duller until it pops in. So that means, though, that you have, like, if you have a whole bunch of colors in this, you'll have like some weird desaturation effects. They're all going to just be smushed over each other. It's going to look really flat because where you used to have a range, you're just going to have a little blob going in. But that's another approach. Now, the other bit was black point compression. So RGB technically has richer blacks than a CMYK will. So it will have a wider dynamic range. In other words, you can fit a lot of stuff in that black. You can see a lot of things. It's like when your eyes have adjusted to the dark. So the black point compression will reduce the blacks so that they will be flattened in order to preserve the range in the CMYK and maintain detail in the darkest colors. So it's a different approach to that, trying to compress that down rather than clip it. All right, so that's what all the intents mean. So it's time to go ahead and apply this thing and take a look at what it does in reality.